So a theory. What is a theory? There's a saying you'll hear a lot. It's just a theory. Well, a theory is the strongest thing we have, the strongest tool we have in science, besides our observational skills and our questioning skills. Since both observation and questioning comes into the development of a theory, obviously those are foundational. But a theory is all we have in science. So you might ask, well, what about a law? I want to remind you what we've talked about already when it comes to theories and laws. That a law is a phenomenon that we observe that is constant, we don't see very many exceptions to it. So for instance, the Newton's laws of motion, those are just laws, those are just relationships between acceleration, between velocity and movement, mass and acceleration, that we've identified. Based on those laws that Newton's observed, theories were developed. So when we look at the theory of evolution, Darwin, who is famous for describing it, it didn't just come out of nowhere. In fact, a lot of the ideas that he came up with had already been observed and described. So what Darwin was trying to explain, which is what a theory is an explanation. All right? So a theory is a scientific explanation for what we observe, for phenomenon and patterns that we see in nature. Theories explain them. And if the explanation is good enough, then we'll be able to predict, and it will help us understand what we see around us. So when we look at Darwin, he came up with this idea, or this theory, of evolution by natural selection. Well, his grandfather, Erasmus Darwin, had defined for Charles the idea that acquired characteristics, what you and I today call traits, we've discussed it, we've mapped them out, we've looked at the different ways of inheriting them throughout the year, the last quarter 3. We looked at what Erasmus said was, look, there are these characteristics that living creatures inherit. This was a big influence on Darwin, and Charles took that with him as he moved forward. Now, one of Darwin's compatriots, one of his contemporaries, not compatriots, but contemporaries, was John Baptiste Lamarck, and Lamarck came up with an idea, with a theory, that explained the differences, and what he was trying to explain is how is it that giraffes have really long necks? Some trees are short and others are very long. How does one acquire a new trait? Today you and I know about genetic mutations, and we've discussed a little bit about this idea of natural selection, selecting a group of traits over another. But in the late 1700s, early 1800s, they had no idea about genes and proteins and how traits are inherited in general. They just they observed that traits were inherited. They observed that strong men tended to have boys that were strong, and tall men tended to have, and women tended to have children that were tall, and certain trees, a pine tree, tended to have progeny that were pine trees. And so they observed that certain characteristics were inherited from their fathers and their forefathers. But they noticed that certain groups had changes, and they wanted to define. They couldn't figure out where did those changes come from. Jean-Baptiste Lamarck argued that it was the environment. He argued that a giraffe's neck got longer as it stretched and stretched and stretched. Its neck got a little longer each time. And when it had a baby, because of all that stretching, its baby had a longer neck. So if we take a look at this baby, here you have these. This is Lamarck's concept, right? That you have two giraffes. One chooses to eat the leaves in the lower bush. Another one keeps reaching for those taller trees. And after some use, it's able to stretch its neck out. Just a little, not as long as a giraffe we see today. And when they have babies, separately obviously, the progeny of this giraffe has a short neck, and the progeny of this giraffe has a longer neck and longer legs. And this continues generation after generation until you have a population that has long necks and long legs. That was Lamarck's idea. He was laughed at for years, many, many years after that. Darwin's idea was much more relatable and had much more evidence behind it. But it turns out that Lamarck had some justification. It turns out that things were not as simple as Darwin had first explained, and Darwin knew that. Darwin was defining these laws of evolution, these observations, into a theory. He was refining it into a theory. But like any theory, over time, he expected it to be refined and improved. No one, at least I don't think anyone, really looks at a theory as being completed. A theory is always something that, in other words, an explanation of how things work. If you think about a theory that way, then you expect that as you learn more about how things work, as technology and knowledge increases, your explanation has to change. And that's why theories change all the time, because as you learn more, you understand more. And as you understand more, you explain it better. So that was Lamarck's idea. It wasn't accepted, and it's mostly not true. But there is a thing called epigenetics, which we'll talk about at the end of the unit. And we talked about already a little bit. There's this layer of genes that get turned on and off, that are turned on and off because of the environment, because of their use or disuse in some cases. So depending on any particular case, a trait or a gene, the environment, the use of or lack of use could influence the gene expression, the trait, and therefore Lamarck had some justification, something to add to the conversation. But the basis of the conversation was more of a Darwin-Wallace view. And you'll see here that this would be what Lamarck would have suggested, that as the short-necked giraffe kept stretching, its neck would increase in length, and its legs would increase in length, and its babies would have longer necks and longer legs, until you have the giraffe that we see today in the population. So here's Darwin and Wallace, and Darwin and Wallace thought, look, it's probably more likely that there's a group of individuals that have long necks, short necks, and medium-length necks and legs, and some factor, for instance, the source of food, maybe the fact that all the leaves are high up in the Serengeti, would allow the ones with tall necks to survive more often than the giraffes with shorter necks. And over time, those giraffes with long necks and long legs survived more often than those who had short legs, necks and short legs. They had more food. They had more availability of food, better able to defend their young, could run faster, what have you. These longer-necked, taller creatures survived more, and that's the population you see. The shorter-necked ones died off and became less prevalent in the environment. So you get a population that you see more often, that whose combination of genes end up being the predominant form. That was Darwin's and Wallace's ideas or theory, explanation of what was seen. Lamarck's explanation just didn't work. The reality was when observations were made, Lamarck's explanations just could not explain what was seen, where Darwin and Wallace's explanation could explain what was seen and could predict future outcomes. So ultimately, it was Darwin and Wallace's view that was the predominant one, which is that you have this group of combination of alleles. Now remember, what is a combination of alleles? Long legs, long neck. Well, how to get the long neck? It has the genes for the long neck and the genes for the long legs. And the combination of alleles that allowed the giraffe to reach the leaves and eat a lot of food was the one that was successful. The one that had the shorter neck became less in number. They became rarer because they would die off sooner. And if they got rare enough, they would leave the population entirely. Those genes would no longer be in the population, right? At some point, if you don't make enough babies, then those genes don't go on. So that's how you can get genes to disappear from a population without there actually being an extinction, right? And if you get enough of those changes, then the population changes from these short-necked creatures that you might call one species to these long-necked creatures that become a different species. Maybe the longer-necked creatures that we call giraffes today just wouldn't have anything to do with the shorter necks. They chose the ones that had longer necks. Why? Because they survived better. And that's generally how evolution works, is that this idea of selection and all the different factors that go into selection impact the population overall, the gene combinations, which then impacts what you see and what we define as a species or a taxa. All right, so that was Wallace and Darwin. But again, where did Darwin get those ideas? Well, Lamarck certainly influenced him. He mostly rejected by a lot of people, although some people did support the Lamarckian way of thinking. Ultimately, it was Charles Darwin's definition and this guy named Alfred Russel Wallace, who they actually came up with this idea of natural selection. Wallace came up with natural selection, which helped Darwin define evolution, right? This idea that the best fit to survive, that when you have a competition, when you have a group of organisms and there's all these different allele combinations, that the individuals that had the best combination for the environment at the time, right, would be the ones that would be selected for by nature. Those would be the ones that would make the most number of babies and would define the next generation and what the next generation would look like. One of the ideas that was prevalent at the time was Malthusian, this concept of Malthus by Reverend Thomas Malthus. This idea this essay he wrote about how populations are going to be limited by the amount of food. And it turned out that human population, even though Malthus makes some really good points, and there probably is some upper limit that we are reaching as a human species now, because as we reach closer and closer to 9 billion on the planet, Malthus said that as your population increases, you're going to run out of food. You're going to run out of the ability to make enough food for the population to survive. And as starvation occurs because of overpopulation, your population would then quickly decrease in a catastrophic way. So Malthus was arguing that for some kind of population control back in the 1700s, he noticed this. This is something that he noticed, and of course people noticed it before him, but he defined it as an essay. Now today, when we look at, now we're not talking about the 1700s, we're talking about the 2020. We're looking at a population that's 7 billion and increasing to 9 billion if we don't do something soon. This overpopulation causes, to some extent, the increased spread of disease, which explains why a place like New York that's so congested, that has such high population density, can have such a quick spread of a disease, which is why you can explain the idea that a lot of flus, a lot of these coronaviruses start in China, a very densely populated country. When you look at the spread of disease, the higher the density of the humans, the higher the density of any organism, the quicker disease spreads, because it's as you can see by the concept of addressing this COVID infection by social distancing. The closer you are as humans, the easier it is for disease, whether it be a virus or a bacteria, to spread from one to the other. And of course, that increases the chances of things to die. And one of the other things that influenced Charles Darwin's theory was this concept of the principles of geology, that the things we see going on Earth now have always been here. They've always moved in the same way. So when you see a mountain increasing in size 3 inches per year, and you see it's 1,000 feet high, then you can calculate how long that mountain's been around by going 3 inches a year times, or 1,000 feet divided by, so you take 12,000 inches, which is how many 1,000-foot high mountain would be, and you divide it by 3 inches per year, you're going to get how many years it took to build that mountain. So anyways, that's just an idea that Charles Lyell defined, coming up with these laws of nature, of how the earth changes. He hypothesized, he came up with these principles that suggested that these mechanisms have always been the same, even before man walked the earth. So however long it takes for a river to cut out a gorge, that's how long it takes. It's not going to go faster or slower as the eons go by. So to Charles, that meant that what we can see, we can explain what we see in the fossil evidence, and we could put a time scale to it. We can explain these changes using all these different people, his grandfather's work, his Thomas Malthus, Jean-Baptiste de Lamarck, Alfred Russel Wallace, and Charles Lyell, all were influencing his thinking as he's traveling on the Beagle, seeing this diversity of life, and then noticing that the populations change and are different in different places, and explaining it by the changes in geology, the changes in the environment, and the changes in inheritable characteristics. Of course, he didn't have the information on chromosomes, right? He didn't have the idea of genes and how genes inherited. That came after him. If you look at the timeline here, you see Charles Darwin died in 1882. Well, at about the same time, he did not have Gregor Mendel's work. Gregor Mendel came up with the ideas and fundamentals of genetic inheritance and had published it in German, but no one really noticed it until much later. And later on, after Darwin's death, people rediscovered Gregor Mendel's work. Welsman looked up and proposed ideas that chromosomes were the basis of a heredity, and that's what we studied this year. That's what we teach you now, that we inherit genes through chromosomes that we got from our parents. And we discussed all that there's 23 pairs of chromosomes. One set came from mom, one set from dad, each of those having different combinations of genes. So Welsman first theorized that in 1834, or not 1834, but somewhere between in the early 1900s. Then the work of all these people on population genetics, from Fisher, Haldane, and Wright, and then Huxley, Mayer, and Dobzhansky, all looked at how can you explain Charles Darwin's theory of evolution using all these different lines of evidence. So they didn't have in the early 2000s, they didn't have until the 1960s, they really didn't have any detailed definition. As we discussed earlier, we didn't even know that DNA for sure was the inheritable material until the 20s. And it wasn't until the 60s that we had an idea what DNA looked like. So certainly after the 60s we could understand how DNA was replicated. Okay, so knowing all this, what I'd like you to do, and if you see here, there's a description of the activity that I'd like you to try to do, is choose one contributor to the evolutionary theory. Don't look at Charles Darwin himself, right? Because enough people have written enough about Charles Darwin that I think it would be not as useful if you just picked Charles Darwin. But just write a few paragraphs and discuss the role of these other people on Charles Darwin's theory, on contributing to the ideas of Charles Darwin. And if you choose one of these people, like Gregor Mendel or Welsman, that came after Charles Darwin had passed away, their contributions all came after Charles Darwin had passed away. Obviously, they couldn't influence his original work, but they could influence the neo-Darwinism, right? The idea of how we take all this information and process it in terms of evolution and natural selection. So pick any of these, and it really doesn't matter who, and write a couple paragraphs on how they influenced the idea of evolution through natural selection. All right, that's it for today.
Hello.